Good day to Dr. Chan. My name is Muhammad Aziz bin Muhammad Rosali. Today, we will be presenting on the topic Comparative Analysis of Single Machine, Docker, and Multi-Machine Word Count Program Execution. In this presentation, we will walk through how each approach works, the differences in their performance. Now, I will start with the motivation of our project. First, shift to microservices. Modern cloud systems move from monolithic design to distributed architectures. It requires efficient service communication. Second, growing performance demands, which is data-intensive applications need faster and more efficient communication methods to keep up with increasing workload size. And last, need for better performance. This project will test REST versus gRPC in word count systems to identify the most efficient approach for maximizing CPU throughput and minimizing network latency. Now, move on into the problem of the project. First, single machine limits. CPU cores and RAM create a hard cap. A single-threaded process can fully use all cores because of software locks. Next, scaling challenge. Scaling up is costly and impractical, while scaling out introduces network bottlenecks between machines. And last, need for efficient communication. When work is distributed, fast and lightweight data exchange become crucial to reduce network overhead.
This slide outlines our experimental setup. We designed four specific comparisons to isolate performance bottlenecks, moving from simple local baseline to a complex distributed system. First, at the top, we compare multi-processing versus multi-reading. This serves as our control groups. It allows us to measure the raw computation speed of our algorithms without any network or protocol overhead. Second, we have a single machine with no Docker. Here, we run the system natively on localhost. This isolates the protocol themselves, allowing us to directly compare the speed of gRPC binary serialization against text-based JSON with no other variables involved. The third one is we have a single machine with Docker. We then introduce containerization. This stimulates a cloud cluster on a single computer. The goal here was to test how the protocol performed when communicating over a virtual Docker bridge network. And lastly, we have a multi-machine, which is this was our real-world test. We physically separate the master and the worker onto two different laptops connected via Wi-Fi. This test how gRPC and REST handle actually network latency and bandwidth constrained across different operating systems.
I'm Muhammad Aisamuddin bin Azizan. I will start running VS Code and I run the project using WSL. So we go to the multiprocessing file and run the Python code. So uh, the result elapsed time is 0.6482 seconds and throughput 7.9986 MB per second. Then I run the code in the multi-threading file. Okay, the result elapsed time is 0.6207 seconds and throughput 8.3532 MB per second. The elapsed time and throughput will be explained in the comparison result section. Thank you. I'm Muhammad Aisamuddin bin Azizan. I will start running VS Code and I run the project using WSL. So we go to the multiprocessing file and run the Python code.
So, now move on into single machine without Docker demonstration. What is single machine without Docker? It is a single machine setup means everything runs directly on one computer using its own operating system and hardware. There is no container, no isolation, just a normal program running on the machine. In this setup, the master process gives tasks to the worker process. All workers share the same CPU, RAM, and file system. So now I will demonstrate how program work in single machine without Docker. So I will do for gRPC first. First, we set the direction into the worker folder first. So we set the first worker to the port 6001. So the first worker listening on port 6001. Now for the second worker, we must create new terminal. We set the direction into the worker folder first. Now we set the port for worker 2 to the 6002. So the worker 2 listening on port 6002. And last, we must run the master Python file in the new terminal. So we can see the result after send the task to the worker 1 and the worker 2. We can see the total unit works, the elapsed time, data size, and throughput, which is speed. So this is the result we get after run gRPC in a single machine without Docker. Now, I will do for rest. First, we set the direction to the worker folder in word count underscore rest and set the first worker to the port 6001. Then, for second worker, we must create the new terminal and save. We set the direction folder for worker in word count underscore rest. So the worker 2, we set the port to 6002. And last, we run the master file in master folder. So after run the master file, we can see the result after the task sent to the worker 1 and 2. We can see the total unit works, the elapsed time, the data size, and throughput, which speed. So this is the result we get after run rest in single machine without Docker.
Hi, my name is Muhammad Arfan Muzami, bridge material number 161508, and today I will explain how we deploy our distributed system on a single machine using Docker. For this scenario, we didn't need multiple physical laptops. Instead, we used Docker to create a virtual cluster right inside one host machines. As you can see on the slide, we have one physical host. Inside it, we use Docker Compose to spin up three isolate containers, which are one master and two workers. The most important part here is the Docker bridge network connecting them. This acts like a virtual LAN cable, allowing the container to talk to each other securely using simple names like worker 1 and worker 2 without needing complex IP configurations. Now, let's look at the workflow. This is where we compare the two protocols, gRPC and REST. Once the system starts, the master container split the text files into chunks and send them to the workers. If we look at the right arrow, for the RPC, the master opens a high-speed persistent channels. It converts the data into binary protocol buffer, which are extremely compact and fast to transmit. For REST, the master acts like a web browser. It wraps the data in JSON text and sends it via standard HTTP POST request. While flexible, this adds overhead because text is larger than binary. In both cases, the worker receives the data and processes it in parallel, completely isolated from each other. Finally, let's look at the result. Once the worker finish counting the work in their specific chunks, they send their answer back to the master, again using either binary objects or JSON text depending on the protocol we selected. The master waits for both responses, combines them into one final global totals, and prints the result, as you see in the speech bubble. Total unit works around 23,723. This confirms that our containerized setup is working correctly as the distributed system. We will show you exactly how this code runs and produce this result in our live demonstration coming up next. So hi, I will now demonstrate the execution of our workaround system. I will run the benchmark twice, first using gRPC and then using RISE, so we can compare the performance. So first I will run the gRPC configurations. I am using the standard commands, docker compose build, this build our image and set up the high-speed binary communication channels. As you can see, Docker is creating the network and starting the master and two workers. The master is now splitting the text and streaming binary data to the worker. And here is the result. For the RPC, the total unit works are 23,723 and the time taken was 0.2 seconds. As we can see in the Docker also, we got this one as it's keep running, the worker 1 and worker 2, and then the master. And now I will switch to the RISE configuration to see the difference. And I will shut this down to clear the environments, which is the command is docker compose down. So for this run, I execute the command docker compose f docker compose YAML. So the system is starting up again. This time, instead of binary stream, the master is packaging the text into JSON and sending it via HTTP post request, similar to how a web browser talk to a server. So here is the rest result. The count is the same, 23,723. However, we notice that the time taken here is 0.2438 seconds. Like the gRPC before, the elapsed time is 0.2. So as we can see, it is slightly slower than gRPC. This confirms that the overhead of formatting data into JSON text make RISE less efficient for high performance computing tasks.
Hello everyone, my name is Rahman Hakim bin Afizal. My matrix number is 163550, and today I'll be presenting about the multi-machine deployment. So before we demonstrate how it works, so I would like to talk about the initial setup. So firstly, we have two devices, laptop A and laptop B. So laptop A acts as a master. Inside it, we use WSL2, and then for the laptop B, there are two workers inside the laptop, worker 1 and worker 2, and it uses Windows 11 operating system. So how it works, firstly, the master send the text chunks of the worker program to the workers so that they can work to process it, and then after they complete, they send back the results to the master. So basically, when worker 1 has been assigned the IP address of 10.202.200.150 with the port number 6001, while the worker 2 has the same IP address but with different port. So the master IP address that we're using is 10.212.203 and 0, which is the laptop A's IP address. So after it's done, two workers will send the result to the master, and the master will aggregate the results, and finally it displays it on the screen when we run the master code. So basically, it shows a concept of data parallelization and doing this process. So without further ado, let's try to demonstrate. So we'll start with REST multi-device scenario. So as you can see here, this is laptop A as a master. So I'm running the, so as you can see here, so I'm running the master command. So it will start to listen for the workers to complete their results. So this is laptop B. So there are two workers. So I open two tabs to represent worker 1 and worker 2. So if you can see clearly, so this is worker 1 that uses port 6001, and the worker 2 is using port 002. So it's running, the workers are running, if you can see here, and then the master is showing the results here. So it's connecting via local area network. I'm using USM Secure during that time. So next, this is gRPC setup. So this is laptop A. So I think this is the complete one, the completed result for the master after the workers have been completed the process. So this is laptop A. I'm going to the laptop B, the worker laptop. Let me, okay, you can see here. So this is this PowerShell terminal represent worker 2 with the port 002 is currently listening. So this is worker 1, port 6001. Okay. So I'm running the master. I'm typing the command, and the two workers are currently listening to wait for master to give the text chunk data for them to work. So when I run the master, it will show the results that have been produced by the workers. So you can see here the elapsed time, the throughput there. So that's all about my pre-recorded presentation and my explanation for the demo. So I hope you enjoy it, and thank you very much.
Hi everyone, my name is Muhammad Haziq bin Sazali and my metric number is 163646. Now we will talk about the experimental output comparison. Our first comparison is between multi-processing and multi-threading. We found that multiprocessing was far superior than multi-threading. It was faster in terms of throughput, and the elapsed time was shorter. The second and third comparison is between gRPC and REST in the environment of single machine no Docker and also single machine with Docker. And for both environments, gRPC was always faster than REST. However, when we moved to a multi-machine environment where the master and worker were on different laptops, the speed dropped significantly to around 2 megabytes per second. So this gave us our first major clue that network latency is the biggest bottleneck in this system. Now, let's proceed with the analysis of our findings just now. Our first observation is relating to the protocol efficiency. Across every single deployment mode that we tested, we found that gRPC consistently outperformed REST. Whether we were running locally, with Docker, or over the network, gRPC was always faster than REST in terms of throughput, and the elapsed times was always shorter. This is because gRPC uses protocol buffers, which turns our data into small, efficient binary format, while REST sends data as a JSON text-based format. So this proves that the binary is more efficient than the text-based JSON format. Our second observation is relating to the infrastructure and hardware impact. You might have noticed something unusual in our results. Our Docker containers ran faster than our no Docker setup. Usually Docker adds a bit of overhead, so it should be slower, but in our case, we distributed our tasks among our group members, and the team member running the Docker task utilized a device with a significantly higher CPU or RAM specifications, meaning his laptop were better than the one that ran without Docker. So the lesson learned from this is that hardware performance differences between laptops outweigh the software overhead of Docker containerization. So hardware specs matter more than the visualization overhead. And our last observation is relating to the network bottleneck. No matter how fast our laptops were, as soon as we connected them over Wi-Fi for the multi-machine test, the speed dropped by nearly 90%. So this confirms that in a real distributed system, bandwidth is the actual limit. Network latency is the great equalizer because it slows down even the fastest machine. To conclude, our experiments point to a clear recommendation for building a distributed system. First, gRPC is always the superior choice for internal communication because its binary efficiency makes it significantly faster than REST, especially when network bandwidth is tight. Secondly, while Docker adds a tiny bit of complexity, our results show that it is highly performant. So the real performance gains come from ensuring your underlying hardware is powerful. And finally, if you are using Python for CPU-heavy tasks like word count, you must use multiprocessing rather than multi-threading. So therefore, our final recommendation is that we should use gRPC to minimize network impact and ensure high-spec hardware is used for all the master and worker nodes. So that is all from our group. Thank you very much, Doctor.